Okay, we've seen exponential growth. We're going to take a look at another type of growth, which we call logistic growth. Okay, so we've seen exponential growth using this equation right here. And if we just change the variables, since we're going to be talking about populations, we're going to use the variable p instead of y, but it's the same thing. So we have the differential equation dp dt equals kp, meaning the rate of growth of that population is proportional to the amount present. And that gives us p equals p sub 0 e to the kt. That's exponential growth for the population. But in real life, there's really no way for a population to grow exponentially forever. There has to be some sort of limiting factor, whether it's space or food, something that's going to make it so the population can't exceed a certain value. We call that value the carrying capacity. We'll call that m. So a more realistic population growth model would be the logistic growth model, where growth is proportional to both what population is present and the carrying capacity that remains. So how many individuals there are in this population and how far are we from reaching whatever max population we have. So dp dt equals k times the current population p times the difference between the max capacity and the current population m minus p. So we can see that we have this exponential growth model, but it's multiplied by this limiting factor. And notice as we get closer to that max capacity, m minus p, that's going to approach 0. And so dp dt, the rate of growth, will approach 0 when we reach our maximum capacity. All right, so take a moment here to just follow along. You do not need to write this down. You will never have to recreate this, but we want to see where our logistic growth model comes from. So starting with our logistic differential equation, we're going to use separation of variables, divide by p times m minus p, multiply by dt, and we're going to use the method of partial fractions. So we have this factored on bottom, so that's equal to a over p plus b over m minus p. Use our methods for solving by multiplying a times m minus p and b times p. Okay, keep in mind here that p would be considered our variable, so if this is all equal to 1, that means 1 is the constant, a times m is a constant, and a equals 1 over m. Since on the left side there is no p, that's 0, equals negative ap plus bp. Divide by p, so a equals b, so b is also equal to 1 over m. So now we can rewrite this as 1 over m times 1 over p plus 1 over m minus p. And I'm going to move that m over to the right side. And now I can throw on my integrals, take the antiderivative, and using our log rules, we can combine those two logs together. We can get rid of the natural log by exponentiating. I flipped around the fraction, which makes my exponent negative. Simplify the fraction. Add the 1 over. So if I solve for p, I get m over all of that stuff on bottom. I can take that minus c out as a constant, and I can write it as multiplication with e to the negative c times e to the negative mkt. And e to the negative c is just a constant. We'll call that a. So we end up with this formula right here for the population. This is our logistic growth model. We have our population at some time t. M is our carrying capacity. A is a constant that's determined by the initial conditions, but it's important to understand that A is not the initial amount. And K is the rate of growth, the growth constant. And like I said, the good news is this formula will be given if it's ever needed. You don't need to be able to recreate it, you don't need to memorize it, but you definitely need to recognize it. Okay, let's say we have a grizzly bear population. We introduce 10 bears. And there are 23 bears in the park at present, and we know that the max capacity is 100 bears. So 10 years ago there were 10 bears, now there are 23 bears. At most it can support 100 bears. So assuming this population grows logistically, we want to figure out when the population is going to be 50, 75, 99, 101. So the max capacity, M, equals 100. The initial population is 10. The population after 10 years is 20. So we can plug these in and try to solve for some of these unknowns. So if our population is 10, initially that's when time equals 0. That allows us to solve for A. So A equals 9. Plug that in. Now we need to solve for K. We can use the fact that after 10 years the population is 23. So plug in P equals 23 and T equals 10. And we can solve for K. Take the natural log of both sides, divide by negative 1,000. There's our value of K. Now putting that all together, we have our formula for this population growth. So to answer the question on the previous slide of what the population is going to be at various times, we could just plug our values of T, or the 50, the 99, in for T right here and find the population. But we're going to take a look at this graphically just to see what this equation looks like. And you can see how as the population gets closer to 100, it levels off, approaching a rate of growth of 0. And if we trace, we can figure out that the population at 50 years, or it should be 50 at 22 years, 75 at 33 years, 99 at 68 years, and the population will never be 101 because the carrying capacity is 100. Okay, we have a group of fish that grows logistically. Here's the differential equation. What is the carrying capacity? Well, we know that the carrying capacity is the value that's going to give us a rate of growth of 0. So if I analyze this formula up above, I have that 50 minus P portion right there. If P equals 50, my rate of growth is 0. So when M equals 50, I'm at my carrying capacity. What is the population when it's growing the fastest? It turns out for logistic growth, the population grows the fastest when it's halfway to the carrying capacity. So when the population is 25. And what is the rate of change of the population when it's growing the fastest? Well, we know that it's growing the fastest when P equals 25. Here's our rate of change formula. Just plug in P equals 25 and solve. And it's growing at a rate of 12.5 fish per year. Now we can represent this equation in a different form. dp dt equals r times p times 1 minus p over m. And I just want to show you that this really is the same formula. If we multiplied by m over m, we'd get r over m times m minus p, and we can just rename r over m, and it's the same formula. But you're likely to see it written in either form, so we definitely need to recognize both of these as being logistic differential equations. All right, so you're given a population that's modeled by this logistic differential equation. And let's analyze some questions here. If the initial population is 3, what is the limit as time goes to infinity of the population? Well, that's really just asking us what's the carrying capacity. As time goes on, what's this population approaching? And this population is approaching 12 because I can see that if I plug in P equals 12, my rate of growth is 0. And so it's kind of a trick question because it doesn't matter what the initial population is, whether it's 3 or 20, the carrying capacity is 12. So if we started with 3 in this population, it would grow to a max capacity of 12. If we started with 20 in this population, it would decrease to a capacity of 12. If P of 0 equals 3, for what value of P is the population growing the fastest? Well, the population is growing the fastest at half the carrying capacity, which is 6.